Welcome back to part 3 of section 2.2. We're going to do just one example today, and it's the application problems for this section. Example 4. The Walters Manufacturing Company needs to know how best to use the time available within its 3 manufacturing departments in the construction and packaging of 3 types of metal storage sheds. Each one must be stamped, painted, and packaged. The table below shows the number of hours required for the processing of each type of shed. Using the information in the table, determine how many of each type of shed can be produced if the stamping department has 3,200 hours available, the painting department has 1,700 hours, and the packaging department has 1,300 hours. So stamping for type 1 takes 2 hours, for type 2 it takes 3 hours, and for type 3 it takes 4 hours. And then for painting it takes 1 hour for type 1, 2 hour for type 2, and 1 hour for type 3, and packaging 1 hour for type 1, 1 hour for type 2, and 2 hours for type 3. So how am I going to get a system of equations out of this? Well, if I look here, this 3,200 is the hours available for stamping. So that must be the total of stamping, and stamping is representing this row. So that means this row is going to equal 3,200. The 1,700 is for painting. So the second row will equal 1,700, and the third row will equal the 1,300. So now I know what my rows are. What are my variables here? Well, we're asking how many of each type of shed. So type 1 would be X, type 2 would be Y, type 3 would be Z. So it would be X's on all of these, Y's on all of these, and Z's on all of these. And if I add these together, I hope you can see how we got a system of 3 equations and 3 variables. So now I'm going to write the augmented matrix. I'm going to cheat a little bit. Since I know I want a 1 on top, I'm going to actually just flip the whole thing upside down. So I'm going to start with packaging, then painting, and then stamping. That way I don't have to do the row swap when I'm doing my row operations. So now let's go over to our calculator, enter a new matrix, put in our new numbers. Use that matrix. Got it correct. So now my top entry, like I said, I already wrote it in such a way that that is my pivot row. So the opposite of 1 is -1 times our pivot row plus row 2. Replace row 2. The opposite of 2 is -2 times our pivot row plus row 3. Replace row 3. Now I'm going to go through -1, row 1, row 3, row replacement. Nope, that's wrong. That's supposed to be -1, row 1, row 2, row replacement. That back button is very useful. Then it's -2, row 1. This is where I hit row 3, row replacement. So I get 1, 1, 2. And if you notice, I already have a 1 here. So I'm going to use that as my pivot row. So the opposite of 1 is -1. times my pivot row plus row 1, replace row 1. The opposite of 1 is negative 1 times my pivot row plus row 3, replace row 3. Go through and do that. Negative 1, 2, 1, replace. Negative 1, 2, 3, replace. It's almost like I picked the numbers carefully so we wouldn't have to do any multiplication. Because if you notice, our next diagonal entry is already a 1. So now I need to cancel out the negative 1 and 3. So the opposite of 3 is negative 3 times our pivot row, which is row 3, plus row 1, replace row 1, and then positive 1 times row 3 plus row 2, replace row 2. And we get our final matrix. So reading this off, we get x is equal to 300, y is equal to 600, and z is equal to 200. But don't forget, we were talking about an application problem here, so I should probably say what each one is. So we get 300 of type 1, 600 of type 2, and 200 of type 3. And that is it for the section 2.2 notes.